the emergent factor is for your instrument. And in the Satlantic software that we're going to be using, there's a switch in the software that you have to tell it whether you're using it in air or in water. And it's important that when you're reducing the data, that you have that switch in the right spot. Okay, yeah.
I have a question about the previous two slides. It might be a dumb one.
No, no,
you
they
can't
aren't.
just take it down on the radius
So this,
thing and flip it.
what's that?
Like, because this is that's between the angles of the issue.
Uh-huh.
And when you're doing upfront,
It doesn't work.
like this and flip it upside down. But that would not be good.
Well, I guess what the point I tried to make was that for the downwelling, you can have a irradiance collector that has large errors at large angles, and it won't matter too much for the downwelling light field in measuring the downwelling irradiance. It will be a problem when you're measuring the upwelling irradiance.
So you should have two different sets.
No, you should have one. If you're going to measure upwelling irradiance, you should have one that's very, it's very accurate cosine response. Works very well out to large angles. And if you have that, you can use it for downwelling too. It's even better. Then you got, I don't know what you
Like just cut it, like measure 100 and you put that, like cut it at 90, and then you have accurate response.
remember, these got a diffuser. It's collecting a whole hemisphere of
Oh, right.
things in there. So, yeah. So you could take a radiance distribution and you don't have to worry about it. You just integrate the radiance distribution. But that's harder. That's harder to do in general. So, okay. So that's that. Here's a blue water, green water. I think he had almost, Kurt showed this same graph, right? So you know what scalar irradiance is. The problem with it, this is sort of a example. The problem with it is trying to figure out, you can't measure the whole scalar at once because you're going to have some sort of an instrument down here that's going to block part of it. So you can talk about measuring just the upper hemisphere part. So you have some sort of a shield that goes pretty far out to block light from coming from this direction, but at some point it will get to your little collection sphere. So there's limitations for measuring the E0D or E0U. So let's see. How do you calibrate an irradiance sensor? That's really easy, roughly. You have a lamp with known irradiance. You put your instrument at some distance, 50 or 100 centimeters. The lamps are typically calibrated so you know the irradiance at 50 centimeters. And if you do a different distance, you can sort of assume that there's a 1 over r squared dependence. And so you can translate between 50 centimeters and 100 centimeters. That's ignoring a whole bunch of details for that you would have to do if you were really carefully calibrating. But it's fairly straightforward to do more straightforward to do the calibration for that. Other calibration problems you can have with an instrument is you have different light levels between the field and the lab. The sun's really bright, so it's really hard to measure a downwelling irradiance, to calibrate a downwelling irradiance sensor all the time in the lab if you don't have a lot of dynamic range. The sources that we use in the lab are much different than the light field you're looking at in the water. So there's the lab calibration sources don't have much blue light, because that's everything we're looking at in the light field in the ocean. You have temperature effects can be in your instrument, so variation between what your field measurement temperatures are and what your lab temperatures are. Scattered light in the lab, you have a 1,000-watt lamp that's shining light everywhere in your lab. You got to try to block off the scattered light, so you're only looking at light directly from the source to your instrument. These are all different things you have to worry about when you're calibrating an instrument. Okay, so remotes, some of the parameters we need to know for this afternoon. remote sensing reflectance. RRS is the water leaving radiance divided by the sky downwelling irradiance, yes. This is the water leaving radiance, is the light that's come out of the water and it's measured above the surface. Or what you want is the light above the surface for this. The reason we want to measure remote sensing reflectance is you want something to relate to satellite measurements, and that's what they're measuring effectively. And it's an apparent optical property, which we'll talk about more. When is the apparent optical lectures? Later in the week? Have we talked about apparent optical properties?
That's tomorrow.
Okay, so you'll talk about those tomorrow. Relatively dependent on water properties, less than illumination conditions. So one of the techniques we're going to do is above water remote sensing using above water instruments. Effectively, you take a radiometer and you point it at the surface. Sort of the good angles right now are 40 degrees. So looking up like this at 40 degrees from nadir and 135 degrees azimuth from the sun. So the sun's over here, so you'll be looking like this at the surface like that. You make two measurements. You make the measurement of the looking down at the surface, which we call LT, where L measured, I guess. And then you'll point the radiometer at the complementary angle looking up at the sky. And presumably that what that is then is measuring the sky irradiance that's come down from the surface, the sky radiance that's come down from the surface from the sky, hit the surface, and some portion of it's going to reflect up into your measurement. So we measure the total look of the upwelling here minus the sky times some reflectance factor to get the take rid of the surface, and the remote sensing reflectance is that divided by the irradiance measurement. So down at the dock, what we have is an irradiance sensor that's going to be fixed, measuring the downwelling sky irradiance, and you'll have a handheld. We're going to make it just a handheld radiometer that will point in the right direction to get this measurement. The reflecting the surface, if you do this, geometry is 0.028. And as long as the wind speed is less than 5 meters per second, which it's almost perfectly glass out there right now. There's a zillion different, here's 3 references. There's a zillion different references for different people trying to figure out how to do this in the best optimal way. In fact, there was another one I saw yesterday that just came out of another analysis of this technique. So I guess if there's a zillion papers coming out all the time, it sort of implies to you that it's not really a settled issue how you should make the measurement. And people are still trying to improve it. It's really, in my view, it's a really nice technique to use in water like this out here, where it's so attenuating that you put an instrument in the water, you're going to get a lot of shadowing because of the instrument being in the water itself. So the above water technique, I think, is really suited for that really well. For clearer waters, personally I prefer an in-water type measurement. So in-water techniques to get the remote sensing reflectance, you make some measurement at some depth they'll use. So that's the light coming straight up, nadir radiance at some depth. Multiply that measurement by the transmission of at the air-water interface, and divide it by ES, and divide it by the transmission, the radiance transmission from the surface down to that depth. So you measure LU, you somehow propagate it to the surface using this inverse of the transmission through the water from the surface to that depth by KL, and then you propagate it through the surface with the Fresnel reflectance divided by n squared, which determines is the radiance, the change in solid angle as you go down through the surface because of refraction. So all this number is about 543. And you measure ES above the surface. So there's a whole bunch of references for this too, but it's pretty well stable how you should do it. And we have the COPS instrument, which will profile which you'll be able to measure, make a measurement of RRS that way.
Could you expand on why the above water is suboptimal and here?
Because the above water, you've got this reflectivity factor here, and knowing for sure what that's going to be. You're sort of assuming that your sky is basically from the one direction versus it's really a whole bunch of directions around there. Yeah, a bunch of it like that.
When I think about all these techniques, I always remember that first always that it's easy to measure, and the complication is usually I mean, a lot of these techniques are well defined for perfectly calm surface. If you have a surface that's modulated by particularly gravity, they're the shortest and steepest way to do it. There's really steep and so they mess up your life. So we have all kinds of nice models for them, and others, but they can be directed in a different way. They will flow light that comes from different parts of the sky into the center. So that's what the above. The water also, you have to there's always it looks like it's easy, but you see places, and then you go as a real and then there's shadow. You're on the boat. The boat is shadowing the skylight. The portion of the skylight doesn't make it sense. So the kind of item is every time you get the measure, you involve it. Less.
The other thing with like the COPS instrument you'll play with, or the Hydro Pro, which we're not going to use on this trip, is you can take a profile in water away from the ship. They've all developed techniques to allow you to do that. Versus the above water system, you're always going to be measuring pretty close to the ship because you got to unfortunately stand and look down. And if you look at some of the ships, you got a big white ship there. Who knows what that's doing to the water?
Anna and I wrote the development very techniques for this, but then you have a simulator level and you 50 degrees field of view. Coming up that direction is very counting. You see every little way.
Yeah.
At least we're away from the ship.
Yeah, and then people come up with ways. Maybe you can use polarization to try to get a better illumination of the surface. But then you got, what are you assuming about the water, the light coming out of the water? How is that polarized? So that's where we are there. Okay, you'll get to play with all of it, but you apparently, and I did this already. There's another technique, Skylight block approach that Jean-Ping Lee has sort of had brought up more lately. That's sort of neat in a way, if especially if you can deploy the instrument correctly. Basically what it is that you take a sensor, but you put it above the surface, and then you have a little cone around it that blocks the light hitting the surface. And if you get everything just right, that'll measure the light coming out of the water above the water, so it's exactly what you want. And then you have the downwelling irradiance that you measure somewhere. So that's a pretty nice way to do it if you can get all of the parameters, get it above in the water, just barely above the surface, and you're not shading a lot of the area around the cone, and it's not so wavy that the instrument drops in the water, or any splashes or whatever. But anyway, that's a pretty, when we've done it out here and what I've seen, it's very, very, the precision is really good if it's the environmental conditions are right. You're just stretching. Okay. And what we have, there's another factor. Another factor we talk about is normalized water leading radiance, which is LW, this remote sensory reflectance. but then you multiply it by E0, which is the extraterrestrial solar radiance. And sometimes there's an R squared for the Earth-Sun distance. But this will put, if you look at remote sensing reflectance, what are the units for remote sensing reflectance? What's that? Steradians, right? Because you've got well, whatever units you want, microwatts per centimeter squared per nanometer is typically what I've used. So you have that per steradian for LW, but then you have microwatts per centimeter squared per nanometer for ES. The only thing left is the inverse steradians. If you that's for remote sensing reflectance. For you put the E0 back here, you get back the microwatts per centimeter squared per nanometer, and you still have these steradians. Okay. Let's see. So there's that. The other thing, there's another technique that's not really like this, but the buoy system, and that's the TSRB, which you're going to play with. And that it's a buoy, has downwelling irradiance and just upwelling radiance at one depth. Okay, and so you're measuring the upwelling radiance at some depth, and you're measuring the downwelling irradiance above the surface. To get remote sensing reflectance, what do I have to do with that upwelling radiance measurement? It's being measured about that deep in the water. What do I have to do to get it to be an RRS number? Not really atmospheric effects. What do I want? I want, what's that? Transmittance. So I somehow have to take that measurement at this far below the surface and bring it up to the surface. And then I have to do the transmitted through the surface, right? Well, we only have one measurement at how deep is it? That's it. 63 centimeters. Okay, you have this one measurement at 63 centimeters. And so we somehow have to get KL to go to the surface. Okay, but you don't have any way to do that, KL. So out here, what do you think is good? Think that's going to be a big attenuation or small attenuation? I wonder how much light we have at 63 centimeters.
The red.
What's that?
The red.
Especially in the blue, I would think. The red, it's probably, is it any different? It's always, yeah. So you're going to have to come up with some way when you make that measurement, determine KL to bring it up to the surface. I don't know, I never got a comment from you about what I put in the lab, right? That seemed to work. I don't know. So you guys are going to try something. I have it in the lab write-up how to try to do a propagation by doing inversion and iteration, and you see how well it works. Tell me. Okay, it'll be interesting to see if it works at all. I'm just saying I came up Sunday night. So, and you'll have KL you can use from the HyperPro to compare to this, so you can sort of see where things are.
There's another organization, and it has to do with the direction of the sun. So they normalize the sun.
Yeah.
The RDF, they bring the
Yeah, and I get it. I'll talk about F over Q in a second. So there's there. So we saw a minute ago, okay, this is F over Q. So the radiance distribution you saw is not uniform, right? It's pretty good in blue water, but it's not uniform. So if I look at the light over here, it's going to be different than if I look at the light there. So you have to have some way, and if satellite, what's it doing? It's looking at a light over a whole swath underneath it. And what it would, almost everybody's measurements are just nadir radiance. So we need to somehow correct for this angular distribution and relate how light, if you view it over here, is compared to if you've been right above it, viewing it straight down. So Morel and Gentili and Antoine came up with this idea of the F over Q ratio. F comes from irradiance reflectance, which was EU over ED, was found to be related through this factor to BB over A. At approximately, F is about equal to 0.33 BB over A. And the reason it was irradiance reflectance versus remote sensing reflectance is that was really popular, especially with the French a long time ago, because all you needed was one spectrometer. You can measure, make a profile with irradiance looking like this and flip it over and do the other way. Oh, you did it this way in your thesis too? I didn't know you were French. Yeah, so anyway, so there's F, so that's where F came from. This having this number R equals 0.33 BB over A is sort of a useful thing to keep in your head. Q is EU over LU. So if the light field was perfectly isotropic, then Q would be equal to pi. In general, it's equal to some number between 3.5 and 6. Clear water is more toward pi. Turbid water is more towards 6. So in general, though, Q as a function of incident solar zenith angle and viewing directions is equal to the upwelling irradiance divided by whatever the radiance in that direction is. So you can have an angular Q. So together you get this factor F over Q, which allows you to relate what you would measure at some varied angle, theta and phi, to what you would have at just looking at nadir. And you can also, through this, make a correction if inside the model, you can make a correction so that you get what the radiance is for solar zenith angle directly above, looking straight down or looking straight down, so the light coming straight up at you from nadir. And so that would be your measurement that you made with some solar zenith angle, some direction, times this F over Q factor. So it's a way to relate measurements from one direction to another. The common model is Morel, Antoine, and Gentili, the 2002, which works really well in clear water, starts to fall apart in case 2 waters. There's a few different methods of papers out for doing more turbid water. Yeah.
What is the difference between case 1 and case 2 waters?
Case 1, okay. Do I have case 1 up there? Anyway, case 1 in general is that in the way I think of it is the optical properties in the water are correlated with the chlorophyll concentration. Okay. Case 2 is everything else. So is that fair? Yeah.
Yeah. And you can think about it like the ocean materials provide products that are being created and created. Where the coastal water, you're not sure what you're supposed to be. Those properties are not correlated with that come from us. So some people will say coastal erosion is not right. Case 1 waters in the coastal environment. You can also have case 2 erosion in other situations. So it really has to do with that. You can model it in a certain way.
Yeah.
We'll talk a lot about case 1 and case 2 when we talk about conversion. Yeah.
Okay. This is a bunch of references, so it's in the talk for the F over. This is the main one for oh, that's probably where did I say case 1 then? Anyway, that's the one that has the model in it, and here's some references that here's a version that works well for more coastal case 2 waters. It's centered on ILPs, and there's a couple more references. Shadowing. We put an instrument in the water, you stay on the ship in the sea, on the dock over here, you're going to be shadowing some volume of the water. We're always trying to, for remote sensing applications, we're always trying to measure the upwelling light, which is being shadowed by whatever we're measuring with. There's several studies on how ship shadow work. Fortunately now for most of our in-water measurements, we do it far enough from the ship so it's not a factor. But instrument shadow is important all the time, and it's usually proportional to the absorption coefficient times the whatever the effective radius of the instrument is. So the idea is you try to use as small of an instrument as you can to shadow as little as you can. So what do you think about shadowing out here in this water? It's going to be huge. Okay, so that's why I said above water techniques are sometimes better as you're doing less instrument self-shadowing. But you should take this into account when you're making your measurements. Think about it. There's various papers that have done calculations of trying to estimate shadowing. Most of them don't take into account Raman scattering. Got to make the pronunciation right. Raman scattering, and so they're not as good above 575 nanometers, but that's also where their shadowing is going to be the largest. So they're all sort of failing there. One last thing I think is a little bit of atmospheric techniques. One way to get at least the simplest optical parameter for the atmosphere is the aerosol optical depth, and use the technique sumphotometry. Effectively, what we have is these handheld microtops instruments, which basically are a handheld, they're radiance detectors, but in the atmospheric world, they say what you're doing is you're measuring the irradiance within 2-degree field of view. The reasoning is when you talk about something like radiance, okay, radiance is the energy per solid angle, right? Is what you want. Now, when I make a measurement of the radiance of something, I want it to be fairly uniform across my field of view because I want that measurement to make sense at all, at some way. If I have a 2-degree field of view, and that's sort of picked by the World Meteorological Organization, because that's sort of, if you're pointing something at the sun, 2 degrees, it gives you a pretty good chance to hit the sun. So you're measuring something with a 2-degree field of view, like something looking at the sun, so that you can get the sun in your field of view. The real radiance varies tremendously across your field of view, right? So it doesn't make sense to call that a radiance. So what we do is it's the solar irradiance, direct solar irradiance that you measure. Okay, so basically you're going to have the microtops you pointed at the sun, and you're measuring the transmit. It's calibrated to know what it should receive if there was no atmosphere above you. You make the measurement at a certain time of day, and you know where you are in the world, so you can predict the atmospheric path length. You compare the measurement you get to what it would have been with no atmosphere above you, taking into account the extra path length, and that gives you the aerosol optical depth. So basically, the irradiance you measure at the surface with that instrument is equal to the one outside the atmosphere times e to the minus this aerosol optical depth times the path length m. So, and the path length m is basically 1 over cosine of the solar zenith, as long as your angle is not too large. So this is the total tau is the aerosol optical depth of the atmosphere. You can split it into a molecular scattering, absorption, aerosol scattering, absorption, and at one point we had a little lecture on it. Usually it gets dropped at some point. To calibrate that instrument, what you do basically is try to take measurements on a very stable day, where as the sun is coming up or the sun is going down. Usually coming up is better because the atmosphere is more stable during that period. The only problem with that, practically, so you're taking measurements early in the day or late in the day here, and then as you get toward noon, you'll be going toward this area. If you have a really good day, it'll be a nice plot, and you propagate this back to 0 air mass, and that gives you your calibration coefficient. the reason you do it this way instead of in the lab is you can't really do it in the lab accurately enough. So you do it this way. The problem with, it's best to do it in the morning as the sun's rising, but you have to start when the sun's very low on the horizon. And if you should someday, if just watch as the sun comes up, you'll notice that early in the day, it looks like the sky is completely clear. And as the sun comes up, you'll notice all these clouds that actually were hanging out all the time. So it's amazing how many times I've gone out and made measurements, got up before sunrise, made these measurements, and then realized that they're all crap. And it was not worth having done everything that day. So.
Are these mostly measured like this to validate atmospheric correction algorithms?
They're mostly, well, like I said, it's a parameter that determines aerosol optical depth is a nice single number that characterizes the aerosol in the atmosphere. By looking at spectral aerosol optical depth, you can get an idea of the particle size in the atmosphere. So this has been used in the atmospheric community for a long, long time. One of the products from the satellite retrieval algorithms is the aerosol optical depth. Unfortunately, when you're measuring it on the surface, you're measuring the forward, have a really dominant part is the forward scattering. For the satellite, it's looking down, so it's most predominantly back scattering. So a good atmospheric correction algorithm that does really well at getting rid of the atmosphere from your images for ocean color won't necessarily be a really good measurement of the aerosol optical depth. Okay.
I guess why are we taking this like aerosol optical depth?
It's because you're characterizing the atmosphere. So if you're going out for a validation cruise of some sort and you're making all these in-water measurements, you also do this to get some characterization of the atmosphere above you, so that when you predict, you give the data to NASA or whatever for validation of their ocean color product, they can check to see, did your if there was if it didn't match too well with the data that they retrieved for the ocean color, was their atmospheric correction off? They can look at the model that was selected in the atmospheric correction, compare it to what you got, and then go from there.
This is one of the data, and one of the issues that are very few measurements about if you don't have a lot of station. Aerosol, length, you have automated station, small all the time. For me, there's not a lot of these are initial coordinates in this respect. Models, check models.
Yeah, if you're going on a calibration or a validation cruise, and you're going out and you want one of these instruments, these microtops, he has a set of microtops he'll lend you if he trusts you, and to go out and make measurements for him wherever you are. I send my instruments back to when I'm going to go on a cruise with them. I'll send it back to him, let him calibrate it for me, and if you have a really well calibrated one, all you do is sit them next side by side and you make the measurements, so you transfer them. And like Emmanuel said, there's these automated instruments called CMOs, which need a stable platform. And those are all over the world making measurements. If you go to aeronet.gsfc.nasa.gov, that's their site, and you can download data. You can look at data from all over the world, real time, or pretty close to real time, at least level 1. Okay, so and if you look at this curve by itself, the slope of the line is giving you basically the aerosol or the total optical depth. And I am ended. Okay, any other questions? Okay. Good. Not too many people asleep. That's good. All right. So 1 o'clock, we'll try to, it's noon exactly now. So by 1 o'clock, we want to start because we have till 2:30 or so without that boat there. And then after that, it'll get a little harder. And also it's supposed to rain at 5. So What's that?